that would be great. Yes,
You want the
corrections.
original with it? I didn't know. I can go
Yes,
staple.
I do want the
Okay.
original.
Can I
Please,
staple this before
please
you
do
leave?
that. Yes,
Alright.
thank you. Thank you. Beautiful.
Is there a stapler? I don't know. I'm about to go find one. Oh, shit.
You can just, it doesn't have to happen right now. Let's just make sure
Yeah,
to.
yeah.
You need a staple also? Nobody in here carries a stapler?
Staple, you-
Jose might carry a
Do you
stapler.
carry a stapler?
I do not.
Oh, it seems like you might.
I agree. He does seem like a carry a stapler guy, doesn't he?
Why would I have a
Because you're very together.
Yeah, I agree.
I know, I was telling my wife, I was like, one of my students, Jose, like, every week he plans out every minute of his week. Teach me sensei. Just don't forget corrections if you got them for today.
I did just staple my corrections.
Oh,
See, I
nice.
didn't staple this to the corrections. I didn't.
You can go get my staple.
He does have a stapler though. I don't see.
Where do you have to go? Like out of this building?
Yeah.
No,
just
that's
this minute.
We're already running late. We're almost start. I appreciate that, but we'll find one after class, or we'll figure out something else.
Go get that stapler.
Oh yeah. Let's settle in. All right. So whatever you're doing, no screens or anything. Even if you're not participating, please just take a minute to settle in.
How do you want that extra credit for doing writing the code?
What about it?
How do we like turn that into you?
Oh, just email it to me.
Okay.
Yeah, perfect. A bunch of folks have, so that'll be good. All right, just settle in. What's up? Yes, sir. Yeah. Not much, just in time. Perfectly timed. You're gonna have to grab a chair, my friend. All right.
While you guys are doing this, I'll attempt to locate a stapler.
Okay, cool, but don't come in until we're done, please. I just ask that, just to keep the room still. Won't be long. All right, close your eyes. And the thing we want to do is make this as simple as possible. The simpler you can keep this, the more powerful it will be. So just feel your body. Let the sounds fall on your eardrums as they are. When you find yourself drifting into thought, just notice the thought and come back to noticing sensation. You don't have to try to fight the thought or blank your mind. If you bring your awareness to your jaw, notice if you're holding any tension there. See if you can soften it just a little. To close this out, bring your awareness to your breath. Notice where that awareness falls when you first turn. See if you can completely be with 2 breaths from start to end. Excellent. Let's come on back. Wiggle the fingers, open the eyes, let the world pour in. Yeah, that was the most rest I've gotten in a long time, so good. All right, my friends. You wanna move, Hoffman? You okay there? You all right? Okay, good. Let's chat real quick after class.
Yeah, of course.
Hoffman's gonna be a math major.
Alright, there's a stapler next door.
Thank you. Just right down there? Oh, in that office
Yeah.
area? Cool, thank you. I'll make sure to get that. Yeah, just, if you forget to get those to me, all good, but let's try to get them to me. Thank you, sir. All right. Anybody know anything about Zeno of Elea? Pre-Socratic Greek philosopher. I so
Sounds
love.
familiar.
It does sound familiar, right? I so love the Greeks. I just finished reading the Odyssey for like the 5th time, just like this weekend. Anybody read the Odyssey? Yeah. You what?
I had to read all of them.
You had to read, yeah.
Iliad,
Yeah.
Odyssey, what was another one?
Huh.
I don't know, like the 3 of it.
Yeah. I'm trying to think of what the other one was, but those are just amazing books. But there's these modern retellings that are incredible. If you're slightly interested, I highly recommend those to you. What's going on there?
I have no.
I'm just watching Jose.
Yeah,
Swan.
so good.
Okay. You guys good? Okay.
So excited to learn about this Greek philosopher.
Yeah. So anyway, this guy is pre-Socrates, and he was a monist. And that meant that he thought reality was just one thing, that there weren't separate objects, that everything was really just this one thing. And he didn't believe in space or time or motion. And he had these arguments that he produced, especially the one that is against the possibility of moving anywhere is his most famous. So it's called Zeno's paradox. This is like, I think like 390 BCE or something like this. It's really a long time ago that this happened. So Zeno's argument went something like this. If I want to start here and I want to get to here, start here, and to get there I first have to travel at least half the distance. I have to travel half the distance at some point. So at some point I make it halfway. Let's call this 1 back here. Now, this is where I want to get, back to the origin, back to the start. But to get there, I still have to travel half this distance. So at some point, I will be at the 1/4 mark. Have to travel half that distance, so I'll be at the 1/8 mark. And there's always another half to travel. So Zeno's argument was, well, how do you get anywhere if there's always more to travel? You always have to travel half the remaining distance. Now, so therefore you can never actually move anywhere. Any thoughts about this? What might be wrong here? Just philosophically, scientifically. Any thoughts on why that argument? I mean, clearly I just did.
Right, like it is technically
Yeah.
accurate.
Yeah, so what's weird, what's like odd about this line of reasoning, or what's maybe
I
a flaw?
I think I agree with this, except
Yeah.
except that the problem is that it's conclusive, but you'll never get anywhere.
Yeah, but I do, right?
But you do get to you.
Some
you
past
yeah,
zero.
Yeah.
You go further than halfway in one step, though.
It's true, But at some point, I'll still have passed that halfway mark. You're right. But I still had to pass the halfway mark, right? That sounds
Are you
good.
looking for something specifically?
No, I'm curious what y'all think. I mean, I've got some ideas about like just physics in terms of acceleration and deceleration and things like that.
Your distance has to close. You have to reach zero.
Seems that way.
Seems that way.
So I guess like I always think that Zeno was thinking that your rate of acceleration was always decreasing, right? Because here I'm traveling 1/2 per step, and here I'm traveling 1/4 per step, and then here I'm traveling 1/8 per step, like that. So my actual velocity is constantly decreasing, I'm decelerating, right? So it's not a constant velocity. When I do this, I'm totally traveling at a constant velocity, roughly. So for me, it's kind of like, it's a cool thought experiment, but it seems a little bogus in a way, right? But it's still a really cool thought experiment, and it has inspired so much. And the philosophers still argue about this. There's still arguments going on about this thing that was produced, 400 years before the turn of the millennium, or whatever, the turn of 0 years.
When we hit zero.
Yeah, yeah. But let's think about it a little bit differently. So in that first step, to travel from there to there, I traveled half. And then I travel another quarter. So after 2 steps, I've traveled 3/4 of the way.
I agree.
Does this all sound good? And then I travel another 1/8, so whatever 3/4 and 1/8 is 7/8. Travel 7/8 of the way. And we keep on doing this like this. So what Zeno's argument is saying is that this sum never really gets anywhere. It never gets to a full 1. So that this is essentially Zeno's argument in mathematical form. That these fractions added up, this infinite collection, this infinite series. Now notice that's different than what we talked about on Friday, whenever it was, Wednesday. Boy, I was like really prescient on canceling class on Friday, right? That worked out so good. I was like, yes, we still got a day of cancellation coming. we can do it. Infinite series, this is different than the things we talked about last Wednesday, which were infinite sequences. And a sequence is a list. A series is a sum. People mess this up quite often. These 2 terms, they're very similar. But this is where we're going to turn our attention for most of the rest of the semester, and we're going to get this very rich, deep theory that's going to actually lend all sorts of really cool insights into just regular functions and their structure. But let's talk about this problem for a minute, because we know damn good and well that you actually do travel the whole distance. But let's try to prove it mathematically. So this problem right here, this sum, really launched modern mathematics, trying to understand what does this mean. And these these sums of numbers, how do you make sense of this? Let's think about that one for a second. So if the laws of mathematics hold for these infinite sums, I should be able to have the commutative property. What's the commutative property? What does that mean? Math major. No, I'm just kidding. Sorry. Commutative property. What is that? Is that A plus B is B plus A? That order doesn't matter. A times B is B times A. Order is unimportant. Does that sound right?
Yeah, that's yeah.
Cool. What's the associative property?
Order does matter.
No, that's a good, I like that, that was a good play, good riff. Anybody remember what?
Would it be that there's different variables, but they equal the same?
Kind of. Yeah, can somebody tell me in terms of just sums? Were you saying something, PK?
A,
Okay.
A plus, A,
Then if I add these two first, then add this, that's the same thing as doing that order, right? The B plus C first and the A. I can associate different groups of things and then perform these operations and they work. What's that?
This is like second grade, third grade.
It's not. This is like, it is in a way, but it isn't. We also have one of these for multiplication that you can group things, do things in different orders and it all works out good. This one isn't gonna be so important, but what's the distributive property? We use this one more than anything.
If you have, you can, is this when you can factor an x out?
Yeah, it is.
X squared is x times x minus 1, x plus 1.
Sure, but I was thinking more, that could be, but we need three things in there. I think what you were saying had.
I was thinking about like factoring in an x.
Yeah, exactly, and that is this. It's the distributive property, but I wanted to kind of ride it out. You can distribute multiplication across addition. But this one here, this is actually kind of a weird one. Modern computers don't always have the commutative property. It's like, say, for example, in Python, when you're doing maybe on a single precision machine, if you were to add 0.1 plus 0.2 plus 0.3, you don't always get the same answer if you add them in a different order. They're off by like this tiny, tiny little fraction because of the way numbers are stored. So we don't always have that in modern computers. You gotta keep an eye out. But the associative property is what I want to look at here.
3 plus 2 is the same as 2 plus 3.
Yeah. Let's take a look at this. So how could I maybe think about this? I could group things in the following way. I could say, let's group the first two, second two, third two. Does that look reasonable? Kind of grouping them like that? So what do I got? What do you think that adds up to? 0. Yeah, seems like, right? Bunch of zeros added together, that sounds right. But what if I held off on this first one, and instead, I started grouping after the first one. So I said, that's 1 plus minus 1 plus 1, plus minus 1 plus 1, plus minus 1 plus 1, and on down the way. 0, 0, 0, 0. So 1.
And what allows you to just keep the 1 without minusing the 1?
I'm sorry, can you explain your question a little?
Yeah, I guess. So I don't know how I'm asking this. Like you have 1.
So I just pulled this.
Oh,
first
wait, you
guy.
shifted it.
Yeah, I'm kind of like
I see.
rewriting. Does that
No,
make
I see,
sense?
I get it
Like
now.
that?
Yeah, I see
Cool,
it. I see it.
cool,
I see
cool.
it. I see it.
I'm glad you asked.
Yeah.
Yeah. So depending on how I did this, I got 2 different answers. That doesn't seem good if things are gonna be sensible. So what are we gonna do? How are we gonna deal with these infinite series? And that's what we're gonna talk about. We're gonna start off today with a very specific one. I do wanna note, and a couple people already saw this, there's a couple of web works up. There was actually one that I put up last week that I forgot to tell anybody about. I spaced out, it's all good. A couple folks did it. Vincent, I think, started, one of you's done, one of you's mostly done. So there's a couple of web works up. There's one on sequences. I think Wednesday's gonna be a day where we get together and work on this stuff, because I created a second one that will open. And this one is on a very certain kind of infinite series. This one, take a little bit. So we'll spend Wednesday just having a work day to knock these out. Questions, sir?
Is the one from last week still open?
I reopened it. Okay. Yeah. And we'll do what it takes to get it done. I promise. So let's think more about this. Let's come back to this because today we're just going to focus on a very specific but incredibly important type of infinite series, geometric series. And the Zeno's paradox is the archetype. This is where the idea comes from. So let's see if we can get a handle on Zeno's paradox. And the way to do this is to look at a thing called partial sums. So this is going to be the nth partial sum of the series. And what does that mean? It means it's the sum of the first n terms. Each one of these is a term. This is the first term. This is the second term. And so on. So each part of the sum is a term, and we just list them in order and give them first, second, third, and so forth. So the nth partial sum is equal to the sum of the first n terms in the series. So what do I mean here? This in particular for Zeno's paradox, let's see, so there's 1/2 plus 1/4. Now look at these bottoms. These are actually powers of 2, aren't they? This might help in figuring out what the nth one looks like. The first one has 2 to the first, second one has 2 squared, then we have 2 cubed, on up to the nth one, which looks like that. Is this making sense so far? Yeah, we're good? Okay. So we're gonna try to actually just figure out what this itself adds up to. And if I told you there's 100 terms, what is the sum of the first 100 terms there? We're gonna come up with a formula for that. And from that, we're gonna understand when n goes to infinity. So let's take just a crazy thing. I'm gonna take half that sum. So notice that when I take half of this sum, what's my first term?
Half of the half.
Yeah, so fourth, yeah, perfect. And I'm gonna kind of write that just to the side. So it's actually gonna add a power of 2 to each denominator. Does that make sense? Half times that makes it 1/2 squared. Half times that is 1/2 cubed.
Yeah.
So this one's gonna look like this. And then eventually I'll get to this guy, but I'm gonna have one more out this way. There's the same number of terms, but they're a little bit shifted to the right. Does that make sense?
Yeah, that part.
Yeah, let me make sure everybody's with me.
Are you gonna explain where that first thing is going, or is that just like?
Oh,
is it
when you say,
gone?
can you ask that question a little differently?
Because I see you have it like intentionally shifted over to the second term. So what do we do with the first term?
Well, that one, so this one
Like, we
just
took
turned
half.
into a fourth. There is no half in this. In this thing, there's no 1/2.
So that like 1/2 to the 2 is that term 1.
Yeah, yes, exactly. First term, second term, third term. So this ends up being the nth term in this guy here. Does that make sense?
Yeah.
Yeah, so this is just 1/2 times that. That's 1/2
Right,
times
right,
that.
right, right.
Yeah. And then on down. Looks like there's a lot of common things here, kind of lined up. I'm going to subtract. I'm going to subtract straight down. So I'm going to take s sub n minus 1/2 s sub n. And what am I going to get? What's left over?
Half.
Yeah, that doesn't cancel, right?
0. Oh.
And then-
just cancel it out. You just get a half. Oh, you get a half plus 1 and plus 1.
Now, what is the actual? What should be here? Because we're subtracting. So
1 over n plus 1.
minus 1/2 the n plus 1.
Oh.
Yeah, does that make
That's what you were like.
That's what I was
Oh,
looking for.
I see,
Yeah,
I see,
yeah.
I didn't realize this.
Sound good? Okay. What's this become?
1/2. That's not.
It's just half s of n equals 1/2 minus 1 over that. And what I really want is a formula for s sub n. I would like a nice formula for it instead of having to go and add this stuff up over and over again on my calculator. So I'm going to multiply by 2, and I get s sub n equals 1 minus 2 over
N plus 1.
2 over n plus 1, and I can simplify that. at this. Does this sound reasonable? So now we have a nice formula that at any point here, the nth partial sum is 1 minus 1 over 2 to the n. Let's talk about this for a second. So now you tell me, what is the first 100, sum of the first 100 terms in Zeno's series there? Well, I'd say it's 1 over 1 minus 2 to the 100. That's freaking big. I mean, that's freaking big. That's freaking small.
Yeah. 1, 2.
Well, yeah, can somebody get a calculator out and just find 1 over 2 to the 100th for us? I doubt we can even get, it'll be an exponential notation, scientific notation. So 1 minus, I haven't a clue.
Oh, wow.
What we got here? Oh, thank you. That's not as bad as I thought. It is
Oh, I was looking for that one.
7.9 times 10 to the negative 31st.
Very small.
Very freaking small. So what is this quantity roughly?
What do you mean, what is it?
Yeah, if I do this math right here, 1 minus that, what's it approximately? Almost 1. Almost 1. Yeah, almost, not quite. It's like 1 minus a tiny little wafer thin piece, right? Almost there, not quite there. What happens as this n gets bigger?
That gets, number gets smaller.
This gets
So
smaller.
it gets further away from 1.
It gets
So it gets closer to
closer to 1.
Yeah, yeah, closer.
Yeah. So let's talk about this idea for a second. I would like to find the limit as n goes to infinity ves sub n. And if I can do that, I've got a mathematical answer for Zeno's paradox. If I take infinitely many steps, each one half the previous.
I was thinking this a bit.
It is a limit. That's right. Good. 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 So let's. This is an important result I'm going to put up here for you. We're going to intuit it. We're not going to prove it, but it's probably going to make a lot of sense. So this is a useful fact, and you will surely keep this at your disposal. As always, on a sheet.
Oh, so this is.
Yep. So, yep. And if Jesus will help you with this, then that's fine. Jesus. Kind of cheating, but pretty sure Jesus has a lot more important things to do than his math. I hope. So let's think about this. R is a fixed number. And maybe we could do a little bit of just rationalization here. So let's say that R is a number between -1 and 1. Let's just start there. So for example, over there, if I had, what is the limit as n goes to infinity of 1/2 to the n? What happens to this quantity, which we just talked about, as n gets bigger and bigger? What are we approaching?
0.
Not 1. Well, 0 here. If I had, yeah, does that make sense?
Oh, the whole, yeah.
Just this guy.
Oh,
Yeah. Does that make sense?
Yeah.
Okay. What about this?
Same.
Yeah, can somebody tell us? Yeah, and this is 0. Can somebody explain why maybe in lay terms? Just like if you were trying to explain this.
Denominator is rising faster than the top one.
Yeah, that sounds pretty good. Yeah, bottom's 4 to the n, 3 to the n over 4 to the n. That's cool. What is it? What happens each time I add a power? I take 3/4 of the previous thing, right? So I'm constantly taking 3/4 of 3/4 of 3/4. I'm always cutting it down. And eventually that quantity is going to head to 0. What if I did this? Limit as n goes to infinity of -1/2 to the n.
Oh, that doesn't go, that goes to big.
same,
Negative
zero.
It does, but it acts a little different, but it does go to zero, right? We're still having.
From the other side, or
Let's do a look at a couple here. So we got negative 1/2 to the first. That's just negative 1/2. Negative 1/2 squared. What's that?
2, or 1, negative 1.
1/4.
A fourth.
1/4.
Yeah, it's 1/4.
Negative 1/2 cubed.
Negative 1.
Negative 1/8. Yeah. What's the next one gonna be?
Negative 1/16.
1/16.
Or
Yeah. And then the next one.
Negative
Negative
1/32.
32.
Now we got the rhythm,
Yeah.
right? Now we can play the piece. So if I were to sketch this sequence out, as we were sketching them out on Wednesday, here's my index. Here is negative 1/2 to the n on this axis. And let's say this is -1, and this is +1. 1, 2, 3, 4, 5, 6. What I'm going to see is my first one, when n is 1, I've got negative 1/2. And then I've got +1/4, and then negative 1/8, and then +16. And I see this thing settling down toward 0. Remember the idea of the strip? You tell me how close, if I claim this thing goes to 0, you tell me how close you want me to get to 0, and I tell you how far out we have to move to be inside that strip. What's up?
What's it called? Epsilon 2?
Yes, an epsilon tube, indeed. So you tell me, yeah, nice. You tell me what your tolerance level is to be close to 0, and I'll tell you how far out you need to go to be in that tolerance. And then you say, well, make a tinier tube. And I go, no problem. I just gotta move out further to get you inside there. But I can get this tube as close to 0 as I want, and eventually that sequence lives inside there. So this idea right here, we can kind of intuit from this that if r is a number between -1 and 1, this limit will be 0, no matter what the fraction is. This is super duper important. If r is bigger than 1, what do you think happens?
Goes to infinity.
Keeps getting bigger, right? So I'm always multiplying by a number bigger than 1. So for example, if I had 1.1 to the n, what's that sequence going to look like? It's going to be 1.1. I think that squared is 1.21. I don't know why I'm putting circles on it. So the list looks like this. 1.1, 1.21. Can somebody get me the next one, please? What's this times 1.1? 1.32?
1.33.
1.33. Okay. Thank you. And then one more for me, please.
1.46. Wait, that times 1.1, right?
Yes.
Yeah, that's 1.46.
Cool. Thank you. And so we see this rising. Now, we don't know for a fact that it doesn't start just kind of settling down, but it does look like it's rising more and more. And if you cranked out enough, you could get this as big as you wanted. If I had something more like 2 to the n, now that one, when n equals 1, that one's pretty clearly going to blow up, just like PK told us, right? Those numbers are getting bigger and bigger all the time. What if the number is less than -1? So like -2, what happens?
It's small.
What does this sequence do?
Is that when it, like, what's that?
Okay, yeah,
It
does.
does go up and down?
Yeah, what's the first term?
Negatives?
Negative
-4.
-2. When n equals 1?
Yeah.
-2, well, 4, -8,
Okay.
16,
Yeah,
right?
I
And
see.
so we're seeing this oscillation that just becomes crazy bigger and bigger and bigger. I can't get that into any epsilon tube that you would tell me. So if you see this sequence, it's going like this, and I say to you, hey, you know what? I think the limit is 5. You say, no, I can make any tube around that. And eventually, nothing's in that tube at all. So this sequence diverges. Then this sequence, or this, yes, this sequence is, I don't want to say infinite because this goes to infinity, but this doesn't settle on anything. It doesn't go in any particular direction. So we just say this diverges. Doesn't converge to anything. This is a super important result. We're going to need that. Because now what we're going to do is look at Zeno's paradox in an abstract light. So far, so good. How are we feeling? Yeah? Good, cool, cool. All right. You good, Othman?
Good.
All right, cool. All right, so now let's look at this problem in general. Actually, let's get a couple sequence properties up, or limit properties that we might need. Suppose that the limit as n goes to infinity of some list of numbers is a. So this sequence the sequence converges. I almost did it myself. And then I got another one, and that converges to b. Picture in your mind, what does this mean? Could someone tell me what that top one means in a sentence or two? What does it mean to say this? Because it's more important that we understand it intuitively. Could someone tell me what this means in terms of closeness to A and the size of n? Think call and response. Yeah.
Does it, like, as n approaches infinity, the value gets closer to A?
Yeah, definitely. Yeah, something like that, absolutely. So let me say it in a call and response way. If this is A right here, and I make a little tube around it, so I go up a little and down a little. So this is plus epsilon and minus epsilon. That's a tolerance level I've set around A. To say this is to say that no matter what this epsilon is, no matter how small it is, I can always find a place in the sequence where from there on out, we're always inside here. So check this out, it's call and response. The call is, can you get it this close? And I say, yes, I can, just move out this far. So it's a game. To say this is kind of we never get to infinity. We never get there. But this is saying, how close, you tell me how close you want to be to this, and I'll show you how far out you got to go to get that close. That's all it's saying. It doesn't say this ever equals A. Not necessarily. Okay, so we got that. So suppose these two things are true. Then the following, then we have this. That if I have the limit as n goes to infinity of some constant times this sequence, so in other words, I multiply each term by the same constant, but I know this happens, then it's essentially just going to k times the value it was settling on to begin with. So if these terms settle down on A, and you multiply each term by k, they settle on k times A. So you're scaling each of the terms, and then the end result scales as well. And this is for any constant k. If I add these two sequences, then it goes to the sum of their limits, like this. And in fact, I could put a minus in there, and that also works. I can do a couple other things. If I take the limit as n goes to infinity of a sub n times b sub n, then this is equal to a times b. And then lastly, just get this last one out. You probably see what the next one is, right? That makes sense. Yeah. As long as b is at 0, if that would be bad, then we're good. Okay, we're ready, friends. We're ready to get a really cool formula or set of formulas out, and then we can crank out a bunch of things and maybe even understand real numbers a little bit better.
I have a question.
What's What's that? Yes, sir.
It sounds like you might not wanna touch on it, but can B ever be zero?
Oh, why would I not want to?
Because you were like, because you were like, only if B, and you were like, move past it really quick.
Well, the problem would be that I would be dividing by 0 in the end.
Right.
And so this might just
I know, I see the
get really
issue.
bad. Yeah.
Does it pop up though?
Oh, yeah, definitely. And we would just say probably the sequence diverges, but we don't know.
We don't know.
I'm just saying definitively, as long as B isn't 0, I can say this for sure. B could be 0, but, and this could work, but we don't know.
Yeah.
Does that make sense?
That's a cool, I like that answer.
All right, awesome. Feels a little less authoritarian, you know?
Yeah, I agree.
You're an anti-authoritarian kind of guy, I know that.
Very true.
So let's look at a general geometric sequence, series. Sorry, general geometric series. And so that's gonna look like this. It's gonna start with some number A. And what's gonna happen is I'm gonna keep adding things, but there's gonna be a common multiple between terms. So to move from this term to this term, I multiply by R. R is some fixed number. To get to the next term in the series, I multiply that previous by R, so it's AR squared. What's my next term?
AR to the 4 cubed.
Cubic, because we're just gonna
You're
do,
just multiplying by single
yeah,
R
just a
every
single R each time. Now I'll get that A to
time.
the
Yeah,
4.
I just didn't know if you were like doing it by the previous term.
Yeah.
Times 2 times 3 times 4.
So we want to study this and understand it completely. This is something we can totally own and understand in every possible circumstance. So we'll call that S. That's we would like a formula for that, no matter what R or A is. And along the way, we're going to get a cool version of a finite geometric sequence. So let's look at the nth partial sum. These partial sums are how we understand any series. Because a partial sum is a list of values that is a sequence. So just make a little note here. Note. The partial sums, or the list of partial sums, these are finite creatures. A partial sum, this is a finite sum. And that we totally understand, and all the laws of math apply. Note that the list of partial sums, S1, S2, S3, is a sequence. And sequences are chill. So we turn these crazy infinite sums into sequences. So let's look at these up here. S1 is just the first term, A. What's S2?
A times N.
What does this mean? Sum of the what?
AR.
Yes, sum of the first two terms. So it's A plus AR.
Oh, yeah.
Does that make sense?
Yeah.
What's S3?
A plus AR plus AR.
AR squared.
Beauty, beauty, beauty. Got it. Cool. Is this making sense? And then what would this be? Anyone care to be bold enough to tell me what to write? I'm drinking real coffee today too.
Can you ask a question?
Yeah, please.
No. Can you ask what you want again?
What is, if those things look like that, what does the general formula look like?
8 times R to the N minus 1.
That'll be the last term, yes. What's the first term? Because notice here, Yusuke, this is a sum. So you didn't give me a sum, you gave me one thing, but it's the last thing. So what do I write?
Would it be A plus AR to the N plus 1?
Not quite.
Plus AR squared.
Plus AR squared, plus,
8RN plus minus 1.
and we don't quite know what n is, right? That's the problem. So I need to leave that, and so at the end, now I put the thing,
N minus 1.
now that'll be the last one.
Yeah.
So notice that if n equals 1, n equals 1, this is just a times r to the 0. There's only one term there, just like this. If n equals 2, the last term is ar to the first. And that looks like S2 over there. If n equals 3, and we know it's going to be just those three, but look at the last term. If n equals 3, ar squared is your last term.
Yeah.
So let's make a little note that there are n terms here, no matter what S sub n is. Let me stop. Does that make sense? Ish. I know it's weird. Does that make sense? Because you gave a great answer there. Do you see the difference between what you said and what?
So does it matter the number of, what's it called, sequences before that?
I also don't understand why like it matters. Do you only need the first 3 in this case? Because after that it's like basically
Oh,
the
like
same.
why did I just write this many?
Well, why didn't you just write AR to the n minus 1?
Because that would just be a single term. So if I said this, that's just a single, that's not a sum. This represents the sum of the first n things.
So the formula also has to be a long sum.
Yes.
Okay.
Does that help a little bit, Yusuke? Does that sound good? Okay, cool, alright. Alright, so we've got this general term here. There are n terms, this general partial sum. So again, keep in mind, this is the nth partial sum. I'm just gonna keep saying this so that we get used to hearing it. Equals sum first n terms. We want to put that in general. Now I'm going to take this thing and multiply it by r. So r s sub n. You've seen this game before. What is the first term here?
R times S sub n?
Yes. What is r times s sub n? So now multiply this by r. What is the first thing I get out? AR. Right? Because a times
Yeah,
r.
yeah, okay.
What's the next one?
AR squared.
Is this good?
Yeah.
Yeah. Next one?
AR cubed.
Beauty.
So on and so forth.
So on and so forth. What happens when I multiply this times r?
Is the first value. Oh, wait,
What is
no,
that?
no, no. AR squared minus 1. So AR.
Multiplied by another.
AR.
Add the exponents. Does that make sense? Okay. But that, yeah, so that's good. So actually, what is the term right before this one?
Before that.
Yeah, what is actually in front of this? Let me back up and get through. AR, what's the exponent?
N.
Not to the left of this, because the exponent's got to go down that direction.
N plus 1.
N plus 1 would be over here.
N minus 2.
Yes! That's it. The exponents go down by 1 as I move to the left. Yeah? So when I take that one and I multiply it by r, what do I get?
AR n minus 1.
AR n minus 1. Just like that guy right there. So at some point, I'll have this term show up here. And then this one doesn't really, this one doesn't have a companion in the original. It's shifted everything to the right by a power of r. Let's subtract. So on the left, I'm going to have s sub n minus r times s sub n.
We get
Yeah, what do I get?
A plus AR n minus 1.
Yeah, yeah.
Minus plus.
Minus
Is it minus? Yes.
ARN.
Yes, AR to the n, yes. Check it out, because cancel, 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 0, there's no 1 here, right? There's nobody as a pair for this one, there's like a 0.
Yeah, so it just
above it.
stays the same.
Stays the same, so it's
But
minus.
negatively though. Yeah,
Yes.
yeah, I see where the minus comes from now.
Look at that for a second while I erase it there. Because now we're going to do what we did with Zeno's game. And I'm going to rewrite this. So the left side, I could use the distributive property and say S sub n times 1 minus r. Check that out. Does that sound right? Yeah, because it's S sub n minus rs sub n. Yeah, I distribute that shit. I'm using those laws. You are, you're waking up. So then this right side, I'm just gonna kind of leave it like that. How do I isolate S sub n? What's my formula for S sub n?
It's
What's on top?
A minus AR
AR and then.
Yes, sir.
over 1 minus R.
Whoa. Oh yeah, never mind, we're good. I see it. I do guys what you're doing.
What is it really important that r is not equal to?
0.
No, r wouldn't be that bad, because then the bottom I just have 1. You're thinking the right way. What should r not equal for this to be? 1. So if, provided r is not equal to 1, because if r is equal to 1, I just divided by 0. So I've got to be careful, yes? Okay, so now let's look at this. Right now, this is a beautiful formula. This is the formula for the sum. This on its own is worth gold. For the sum of the first n terms of a geometric series. You will want this. You will need this on that web work. A lot.
Is this a general formula?
Yes, sir. Absolutely. Oh, so now it's worth writing down? Okay.
Well, I think
You only general formulas, my friend here. All right.
I'm supporting the general formula writing down only.
Yeah, it's fair enough. Fair enough. And then we could keep it on a piece of paper next to us if we needed it. So the legend goes. So let me kind of write this in a different way. I want to show you this. This A is actually the first term in the series, right?
Yes.
It was the first term. So this, S sub n, equals the first term. And we could, let's do one little extra action here, because I could rewrite the top, I could factor out that A, right? Now don't be getting crazy ideas thinking that there's any cancellation that will happen there, because there isn't. Okay, let's not do that shit. Please do not cancel. We gotta leave them like this. So it's the first term times 1 minus the common ratio. This is the Lay formula to the nth power over 1 minus the common ratio. That is a really powerful way to think about this. And it's going to make your life so easy. Let me show you how. Feeling pretty good for a guy who hasn't slept in 3 days. Not too bad.
Jose was not here for that story.
Oh, and yeah, well, we'll tell him after class.
Sure.
Yeah. Things are rolling too good right now. So let's do an example. Find the sum (1 plus 3 plus 9 plus, let's see, what's the 27 plus 81 plus, well, hell, let's just do that. Nice and simple, we don't have to get too crazy. Now, we could clearly add that up, right? This isn't rocket science or even calculus. This is the math from grade school.
This is second grade.
This is freaking second grade. But we're gonna make it so complicated it couldn't be taught in second grade. We're gonna use that formula. So the formula says the sum of this, well, let's see, how many terms are here? 1, 2, 3, 4, 5, right? So there are 5 terms here, so n equals 5.
Oh, sorry.
See how I'm figuring this stuff out? A equals what?
1.
1. And what is my common ratio?
It's 3.
3.
Yeah.
right? And you can see that times 3, that's what you check, just to even see if a series is geometric. Just look at the terms and say, do I multiply by the same number always to get from one to the next? So I go to my formula, and it says the sum here is equal to the first term, which was A, times 1 minus the common ratio to the number of terms over 1 minus the common ratio. And I crank this out. Now I gotta know what 3 to the 5th is, which is almost harder than the original problem, but hey, let's do it. So this is 1 minus, I'm just simplifying again, over -2. 3 to the 5th, let's see, so that is 3 squared times 3 squared times 3, 9 times 9, 81 times 3, 243, 1 minus 243 over -2. 1 minus 243 is negative 241, 242 over -2. That's an easy one to do, 121. Is that? That doesn't look true. Wait, is that true? It doesn't look right. What do we got here? Let's see here. Did something fuck up? 4.
3 times 3 is 9, 9 times 3 is 27, 27.
Yeah, let's add these up. So what is that times that? That's
That's
1.
right, that's right.
It is right? Oh, thank God. Like, holy
That would have
fuck.
been awkward for sure.
That would have been a little rough. I would have blamed it on no sleep, so I got that to fall on.
Ironically, after you said you felt really good, right?
Correct. All right, so let me give you another one. Find this sum. 1/2 minus 1/4 plus 1/8 minus 1/16 plus 1/32 minus 1/64 plus 1/128. What is the let's do this one together. First term,
1/2.
1/2. Common ratio,
A half.
negative 1/2. We oscillate, right? Positive, negative. And then how many terms? 7. Find the sum, please.
Negative 1/2. Wait, the common ratio is how many numbers?
No, the
No,
common ratio is,
is that, negative 1/2.
yeah, what you gotta multiply to move from one term to the next.
1/2.
You think you got it?
Maybe.
Well, check it out. Let's see here. So this would be S sub 7. Sum of 7 things here. And first term is 1/2. 1 minus negative 1/2. You gotta be real careful with that. Use a parenthesis. And then that's gonna be to the 7th power over 1 minus negative 1/2.
Can you not add?
Yeah, so we will add. Yeah.
I put it as an addition sign.
Yeah, awesome. Okay, so we got 1/2 times 1 minus 1 over, let's see, there's 128. So this is negative 128, I think. Is that right? 2 to the 7th. 2 to the 5th is 32. It's computer numbers, right? 2 to the 6th, 64. Yep. That's that. And then this is 3 halves in the bottom. And so the top becomes 1/2 times 1 plus 1/28 over 3 halves. I'm gonna multiply top and bottom by 2 just to clear out those halves there. So this is 1 plus 1 over 128 divided by 3. And so then that is, oh my gosh, 129 1/28 over 3, And then that is 129 over 3 times 128, which is, God knows, 4, 2, 8, 384. Anybody have a decimal version of this? I figured you guys didn't use fractions.
0.3359375.
What was it, Kevin?
335, 9.
335
Okay, that's good enough, yeah, thank you. Anybody else get that number? Sweet. This, I like to think of this as kind of an alteration of Zeno's paradox. Take a half step forward, take a quarter step back, go forward an eighth, go back a 16th, go forward a 16th, and you just keep doing this little cha-cha until you just narrow in on some spot, and this tells you what you're getting close to, how far you'd end up traveling after all these steps. Good. All right, let's try taking this to the infinite level, because we can do this before the end of class. So now, for the infinite version, now again, this is for finite. This is a finite sum. We're going to take this to the infinite level. So the infinite version, and this actually gets way sweeter. You're going to like this. The infinite version. So in other words, I've got keeps on going. Number of terms, infinity. So the way to proceed is to realize that this is the limit of the partial sums. Remember, the partial sums are the first n terms, and then we're letting the number of terms go to infinity. Well, what's the formula for the partial sums? It's right there. So if we can compute this limit of this, we can figure this out. So this is limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. And again, r is fixed. Let's look at this beast right here. The limit as n goes to infinity of r to the n equals, let's write a little piecewise version of this. If the magnitude of r is between 1 and minus 1, what is this limit? 0. So it equals 0 if the magnitude of r is less than 1. If it's a fraction, could be positive or negative fraction. If in any other situation, especially if r equals 1, that's terrible. But if r is bigger than 1, this thing goes either to infinity or it oscillates to plus minus infinity. So it diverges otherwise. So that means this sum, yes, it would if r was bigger than, yeah, exactly. So we have to have r between minus 1 and 1 for this to make sense. So this, if and only if the magnitude of r is less than 1, and again, just remember, that's a double inequality that looks like this. Sometimes people get freaked out about absolute values, so this helps. That limit, this piece is going to go to 0. And we just get a times 1 minus 0 over 1 minus r. That's the sum.
Wait, that's the formula for.
That is the formula. Yeah.
That does make sense.
So let's see. Let's check out Zeno. Let's come back. Check out Zeno. So Zeno gave us this problem. We have this sum. What is r?
Well, half.
Half. Less than 1, right?
Yeah.
So this is, we check this.
Yes.
Yes. So we proceed. If that's not true, we stop. Halt the program.
Yeah.
Right, diverge. Good, we're done with the problem. Right? Now we gotta do more work. It's okay, it's easy work. So the sum, well, let me write this one more way. This is the first term in the series over 1 minus the common ratio. Okay? So S is equal to, what's first term?
1/2.
1/2?
1 minus 1 half. So that would make 3 halves. 1/2 positive.
What's the bottom?
So take half away. Minus 1/2 positive. Is it not?
Yes, one.
One.
So yes,
Yeah, positive 1/2.
positive 1/2, we agree?
1.
1. We get there.
We get there.
We get there. So now let's go back to the Zeno's cha-cha. So here's Zeno's cha-cha. It's 1/2 minus a quarter. Go forward a half, come back a quarter, go forward an eighth, back a 16th. Can you do me a favor and find that sum? First off, what's R?
1/2. Minus negative 1/2.
Yeah. Is everybody seeing how to get that
Yeah,
R?
I do.
Yeah. And so what's my first term?
1/2.
So now it converges, right?
Because negative 1/2.
Yay.
Half over negative.
Yep, so 1/2 over what? 1 minus. Yep. 3/2, yeah, 3/2 at the bottom. But now PK, what's that actually simplify to?
4.
No.
1 over
1 over 3. Multiply top and bottom by 2. That's cool, I just wanted to make sure we were straight up.
Oh, yeah.
So this game where you step forward a half, back a quarter, forward an eighth, back a 16th, lands you at a third of the way across.
The entire distance.
Yeah. If you do it forever and ever. But you can get as close to a third as you want by just following this out as far as you need. Let's see, I might have one more thing here for you. Let's take a look. Oh yeah, let's look at this. So, you know repeating decimals? You know those.
Little lines. 2, 3, 3 lines.
Yeah, with the line. Yeah. This is actually an expression that means 0.135, 135, 135, right?
Yes.
Cool. Keeps on going. Let's turn it into a fraction.
A repeating decimal to a fraction.
Yeah. So this is actually 135 1,000ths plus 135 10,000 or 1 millionths.
Millionths, but it's a 16.
Yeah, think so?
I agree.
Yeah.
I agree.
Now let's actually, so now let's start getting smarter here, because this is actually 135 over 10 cubed. I want to look for a rhythm, and it's easier to do it. What's the next one? Yep. Cool. This is a geometric series.
Yes, it is.
What is the common ratio?
132.
Careful. 135 is not part of the common
10,
ratio.
That's like a 10 cubed.
1 over 10
Oh,
cubed.
1 over 10
Yes.
cubed. Yeah.
1 over 10. Does everybody see that?
Yes.
That's the only moving piece here. What's
What is it? 1?
What's that?
What is it? 1?
So how do you get from, what did you have to multiply to get from here to here? Yeah.
I see it.
You see it now. Awesome. What's the first term?
I was also running away from the fraction part.
135.
10 to
This
the
cube.
cube.
0?
8 to the cube. No.
No, here's my,
Oh, okay.
you're thinking too deep. Just grab that dude. Yeah? Does this series converge?
Let's see. R is less, is greater than 1.
Yeah.
So no. 130. Converge. Yeah. No, it does. No, it does. No, it does. No, it does. No, it does.
It does. PK, why, PK?
Because the bottom is getting bigger, so the whole thing becomes smaller.
Yeah, but let's think in terms of this condition here, right? What is R? It's 1 over 10 cubed, and that's less than 1.
Yeah.
That's all we need. Don't have to think, it's good you're thinking about limits, but we don't have to think that fancy. So here, since the magnitude of r is less than 1, it converges.
Which falls under the geometric series
Correct.
rules.
So I can add this thing up. It's the first term
It's 10/30.
over 1 minus the common ratio. Let's simplify. Multiply the top and bottom by 10 to the cube. You see that? So this is 135 over 1,000 minus 1. Can somebody get a calculator out and check me out? There we go. That's what the man said, right? So that's pretty cool. I'll just show you a really quick way to do the same thing, and then I'll call it a day. I know we're 1 minute over, but just give me a second. If someone gives you a repeating decimal, like, and asks you to convert it to a fraction, you can always do that. These are actually rational numbers. These are just fractions. So the way to do it is to say, okay, well, that's my x, or my x is this. And then you write it out. And you know it keeps going. What do you have to multiply by to get the decimal to the next repeating spot? 10 squared cubed 4
10 to the 5th.
So 10 to the 5th.
What way is it 1 over to the 5th?
What's that?
Is it not 1 over?
No, I'm just multiplying this by 10 to the 5th. And see what I'm doing? Then I'm getting a decimal, a whole piece out front. I want to move the decimal over.
yeah. I see
Just
what- I
one
see what you're doing.
repetition.
I gotcha.
And then subtract. This becomes 10 to the 5th minus 1. And then this becomes just 1, 2, 3, 4, 5. Cancel, cancel, cancel. This is what, 10,000? No, 100,000? No, yeah, 100,000. Is that right?
That's a. Yeah.
Yeah, 100,000. So
5 zeros, yeah. Okay.
yeah, thanks. Yeah, so that's 999x equals 1, 2, 3, 4, 5. So x itself was 1, 2, 3, 4, 5 over
Divided by 999, whatever. 999.
Yeah.
A
bunch of
nine repeating.
Oh, one more 9. I forgot. Yeah, there it is. All right, friends. Cool. So feel free to start on the 2 web work assignments if you haven't. Come on in Wednesday. We'll chat and work.
I think if we do this Sunday or Friday or Monday.
I think I've got it due for Sunday.
That's a good day.
It seems like a good day.
Good day.
And we're gonna just work on Wednesday. And then we should be able to knock it out then. Thank you, gentlemen.
Caduce was like so detrimentally upset to hear about that.
Staples and
Yes.
exams, don't forget. Next door.